Let's take a look at this problem, which consists of a charged composite cable under the ocean. So the problem statement is that we have a long uniform cylindrical cable with a core of constant charge density up to a radius r equal to a, and from a to 2a there's a variable charge density, and the requirement is that there be no field outside the cable. The problem is to find one of the constants in the charge density outside in the outer sheath A in terms of rho naught, which is the charge density of the inner core part of the wire. In all these problems, the word long should be interpreted as infinity. So let's draw a sketch of the cable. It's not possible to draw the infinite cable, so we'll just draw a portion of it and indicate what's outside on either side by those dotted lines. Now the cable has two parts, so we have to go to the new radius, which is 2 times the inner radius, and that also extends off. Now this problem is a classic Gauss's law problem, and there is no other viable method that we can possibly use to address it. So we have to draw Gaussian surfaces everywhere. The appropriate Gaussian surfaces to draw are going to be cylindrical coaxial cylinders to the axis of the cable itself. So let's proceed and draw them. There's one inside the inner portion of the cable. There's one in between, which means in the outer portion of the cable. There's no cavity anywhere. The inner part is filled with charge density rho naught, and the outer part is filled with this variable charge density A over R, and outside there is vacuum. Well, not quite. It's in the ocean, but we can think of it as vacuum. There's a third Gaussian surface which I will not bother drawing because I don't have space, but that's the Gaussian surface we really need to use to find the charge enclosed. So I will use this Gaussian surface, but I'll use r bigger than 2a to study that. So these Gaussian surfaces are all indicated by the standard variable r. You don't distinguish them with further variables like r1 and r2. You don't do that. These cable dimensions are a and 2a, like that. Now on the Gaussian surface itself, by symmetry, the electric field is going to be pointing always radially outward, but the area elements will be pointing in different directions. On the curved surface, the area elements will be pointing this way. On the right surface of the cylinder, they'll be pointing like that. On the left surface, they'll be pointing like this. So let's quickly dispatch of the left hand side of Gauss's law. So Gauss's law is our strategy. Gauss's law says that the closed double integral over these Gaussian surfaces Si, where I equals 1 and 2, E dot dA is going to be equal to the enclosed charge divided by epsilon naught. Now these Gaussian cylinders have to be finite, otherwise the enclosed charge will become infinity. So let's put also the length of the Gaussian cylinder here. Let's call it L. At the end, we want the L's to cancel out. Be careful about that. We cannot have any dependence on L. Only variable that can appear at the end is this R and A. the left-hand side of Gauss's law can be dealt with as usual in these cases with cylindrical symmetry. So let's quickly run over that argument. I'm going to get the left-hand side, which can be represented as the electric flux closed, is going to be the double integral over the left surface. Let me call this dAl and dAr and dA curved, E dot dAl plus the integral over the curved surface, E dot dA curved, plus the integral over the right surface, E dot dA right. Of these two, they go to 0 because the electric field is always perpendicular to the area vectors for the left and the right face. So those go to 0. I put the 0 through the dot product to indicate that it's the dot product that's the reason for there being 0, because cosine of 90 is 0. That just leaves us with one contribution to the flux. Now if you look at this, E dot dA everywhere on the surface of the cylinder, the curved surface of the cylinder, is going to be parallel. So that gives me E dA cosine 0 degrees. Now I can also pull the E outside because it only depends on R and not on the other variables of integration. The other variables of integration in the cylindrical coordinate system are the Z coordinate and the theta coordinate. The area is a integration over the Z and the theta coordinates because that's what gives you the curved surface of the cylinder. But E does not depend on those variables. So I can simply take it out and write E as a function of R to emphasize what I just said. And then I have this. Now the curved surface area of a cylinder is not something that you really need to do using double integration over the Z and theta variables, although if you feel like you can do that. And those who have multivariable experience should actually exercise some of their muscles, because if you don't use it, you lose it in these things, to verify these answers. But it's really not necessary. We know what the curved surface area of a cylinder is. So this pen is a cylinder, and the curved surface area is just the circumference times the length. So that circumference is 2 pi r, and the length is L. So that's the left-hand side of Gauss's law. And once you've done the left-hand side once, you can pretty much keep using it in problems unless you want to demonstrate it again to somebody who has never seen it before. So I'm going to now use this to address the right-hand side. The right-hand sides have to be integrated. So let me call this charge enclosed by S1 Q1 and the charge enclosed by S2 Q2. So Q1 is going to be the volume integral, so from 0 to R of whatever volume is inside, and that's rho naught, volume charge density is rho naught, times dV. What is dV for cylindrical geometry? Well, that's something that you can decide also without really memorizing any formulas. The volume element is the actual volume of the cylinder. Well, that's the area of the cylinder times the height. The area of the cylinder is pi r squared, and the height is just L. So the volume element dV is got by differentiating this. That gives me 2 pi r L dr. Done. So you never have to remember these things. It's integral 0 to r rho naught times 2 pi r L dr. So that gives me 2 pi r L rho naught outside, because they're all constants in this game. So that gives me r dr inside. That's an easy integral. It's just r squared over 2. So I get 2 pi r L, sorry, no r there. There's no r outside. 2 pi L rho naught. So let me just, I was a little hasty on that one. So the 2 and the halves will cancel out next, because r squared over 2 is the evaluation of this integral. The lower limit doesn't contribute. So I get pi L rho naught r squared. Q2, well, this is Q1 enclosed by the Gaussian surface, so Q2 will be the total charge enclosed by Q1. So I'll write this as Q1 as a function of r, because that emphasizes that we're talking about the Gaussian surface and not the total charge of that portion. It's going to be Q1 as a function of A plus whatever new charge is enclosed by the portion that's not, so I'm talking about this portion, because this is the portion that is not in the core. So whatever is in the sheath will be the next thing that you add, and that's going to be integral from A to R, because that starts from A and ends at R, the other charge density, and that's A divided by R times dV, which is the same thing, 2 pi r L dr. Observe that the r's cancel out, and I get Q1 of A is just that one with A replacing R. So that I can just write that immediately, pi L rho naught A squared, plus this is a very trivial integral. You'll notice that it doesn't have any R dependence whatsoever because R's cancelled out. So I can take 2 pi L A outside. And then I have integral of 1 times dr, which is just R between the limits A and R. So this gives me pi L rho naught A squared plus 2 pi L A R minus A, if you evaluate the upper limit minus the lower limit. So that's the charge enclosed by the Gaussian surface S2. Now Gauss's law, we have still not used Gauss's law, we have just been doing the left hand side and right hand sides separately. Now putting it together is when we use Gauss's law. So Mr. Gauss said you take the flux on the left side, calculate it this way, and set it equal to the charge enclosed divided by epsilon naught on the right side. So that's the program we're going to follow. All right, let's do this. For the surface S1, I have E of R times 2 pi RL equals Q1, which is pi L rho naught R squared over epsilon naught. Observe that one of the factors of R's cancel out. Your L, which should not appear, also goes away. There's a pi that cancels out. So all said, E of R inside is just rho naught R divided by 2 epsilon naught. If you want to make this a function of vector answer, you can just do that thing. I just did put a unit vector, and that becomes a vector answer. And this is valid as long as you're inside the core. For the surface S2, we have E of R times 2 pi RL equals this one. So it's a slightly more elaborate thing to write. Once again, you have the L's cancelling out. There's a pi that cancels out, and then nothing else. So we can just solve for this one. It's a slightly more cumbersome expression to write. So I get rho naught A squared over 2 R epsilon naught plus this term here. If I divide the R into these things, I'm going to get the 2 here will cancel out too. So I'll just get A 1 minus A upon R over epsilon naught. I hope I did that right. So let's see, I took the 2 down there because that cancels out, and I took the R down there, which then goes inside and does that. So I believe I got that right, and then you put the R hat outside. So that's the electric field inside the sheath. So I'll say that's 0 less than, A less than or equal to R less than or equal to 2A. Now the electric field exactly at 2a needs to be 0. 2a and beyond needs to be 0. So that's the main condition that we have to enforce to figure out the relationship between these two. So let's do that. What's needed is the electric field at 2a is 0. So I'll put that here. When I put r equals 2a, I'm going to get rho naught a squared over 4a epsilon naught. And the other term is going to give me a over epsilon naught times 1 minus a over 2a. There's some cancellation that occurs. Epsilon naughts will not contribute because of the 0 here. So I'll end up getting rho naught a over, let me just write epsilon naught anyway, 4 epsilon naught equals negative a over epsilon naught 1 minus half, which is also half. So epsilon naughts can now be cancelled, and I get that the answer is that a equals negative, because that's what I want to find. I want to find out what a is. So a equals negative rho naught little a divided by 2. That's a condition for electric field to be outside the cable and not attract wildlife. So let's make sure that the units are right. That's always the one thing that you have to do in these problems to make sure you're not made any mistakes. The units of rho are coulombs per cubic meters. And that's going to be the units of A divided by the units of R. So I get coulombs per meter cubed equals the units of A divided by meters, because that's the units of R, which tells me the units of A are coulombs per square meter. Let's see if that makes sense. Rho naught is measured in coulombs per cubic meter. So coulombs per cubic meters times meters is coulombs per meter squared. So that makes sense. Now, how does the negative answer make sense? Here, it's best to draw a plot to understand what's going on, because a plot always, figure is always worth a lot of money in these things. So here's the electric field, and here are my crucial values, a and 2a, and then beyond that, it's 0. So what does the electric field look like? From 0 up to a, it's a linearly increasing function. So it looks something like that. And then it attains the maximum value over there. And from that point onwards, it's just decay. You need it to go as 1 over r, and there's a small amount of growth because of a over epsilon naught. But notice that if rho naught is positive, then a is already negative. So the whole thing is going to come out as being just a decay. And then it's going to decay down to 0, and it goes to 0 after that. So that's the electric field profile of this problem.